that I'm listed on the schedule, those are just continuation of my grad course. Um, because yeah, it's just what that is. There's no abstract. It's just the continuation of the course. Um, yeah, otherwise, I guess the registration's over there. Probably did that already. So we'll just get started with our first lecture by John Anderson, and I guess we'll go 10 minutes over to make up for starting late, but take it away.
Okay, well,
Yeah.
thanks, Yakov, for the introduction, and thanks so much for, to Yakov and the organizers for organizing this and for inviting me to speak. Um, I'll be talking about, uh, you know, ju yeah, I should say my goal is to just try to, introduce some of the, uh, some of the common tools that are used in studying long-time behavior of nonlinear, wave equations, which is a common thing that comes up in general relativity. But my goal is to do so in sort of the simplest setting I could possibly imagine. So, sort of the uh, plan for the lecture is I'll just study sort of three problems in increasing difficulty. And for each problem, there's just a couple of ideas where if you understand those ideas, you can implement them to do what you want to do. And so just to sort of orient you from the beginning, these will be the three problems. Um, and for each of these three problems, my goal is going to be to prove basically the same theorem. Let me just go ahead and state it for you. So the theorem is, all it says is the trivial solution to these three equations is globally stable. So global, and in fact, asymptotically stable. So I'll say global asymptotic stability uh, of the equals solution. Um, so, really, in case you haven't seen something like this before, let me try to make this a little bit more precise. Let me just tell you exactly what I mean by that. So, uh, for some constant epsilon greater than 0, sufficiently small, uh, we'll be able to prove the following. If B naught in H100 plus B1 in H100 is less than or equal to epsilon, B naught X X. Mm. So let me just finish writing this and then we'll sort of go through it. Okay. So, let me just sort of go through this and explain what I mean here. So I have, these three equations. I'm always thinking that I'm solving these wave equations in the case of three spatial dimensions, which is sort of well motivated for obvious reasons. And I want to understand what happens if you perturb the zero solution a little bit. So I'm going to perturb the zero solution by taking data which are compactly supported in the unit ball, meaning they're very localized, and they're very smooth, meaning that this H100 norm is bounded. It doesn't really matter so much the exact number here. I'm just trying to say that they're very smooth initial data. All right. And if you pose such initial data, the resulting theorem says that the solution exists for all time. These sort of energy-based norms remain uniformly bounded. And moreover, you go back to the zero solution in some sense, meaning that a bunch of a bunch of quantities go to 0 point-wise. All right. Okay. So I'll just jump right in.
Sorry, can you say for the last norm, what is this norm? This is L, yeah.
So I mean, another way to say this is W 75 infinity in X. So this is, I take a bunch of derivatives, not the same number as there, fewer, but those derivatives pointwise go to 0. Okay? Yeah.
I did.
No. So none of these numbers are optimal. They're all chosen to be large. Something about this number does matter. But you'll sort of see in the course of the proof. Morally, what you're trying to show is that very smooth and very localized initial data lead to global solutions, which in some sense converge back to the zero solution. Right?
Do you mean your H100 to include L2?
Yeah, I mean, because they're compactly support. Yeah, but okay. All right, so, we're going to start with sort of the simplest case of this, which is equation 1. And I'm just going to assume stuff from sort of an introductory PDE course, like a first graduate PDE course, and some stuff from maybe functional analysis, like Sobolev spaces, Sobolev embedding theorems and such. So for this, I sort of think that there are 3 tools that you need. And I think that this is a good setting to really see the use of those tools in a very simplified case. So the first tool is energy estimates. And, maybe I'll just say that this is energy estimates part 1, because they'll get more complicated for other equations. Second tool is weighted Sobolev inequalities. And the third tool is bootstrap argument. Okay. So let me just, start by discussing each of these tools sort of one by one. Luckily, the first one is very simple. So tool 1. This is something that you see in an introductory PDE course. You have a wave equation. You just multiply by dt phi and integrate by parts between 2 constant t hypersurfaces. So and what you end up seeing is the following. So integrate by parts between t equals 0 and t equals s. And what you see is the following. 1/2 times the integral over sigma s, where by sigma s, I just mean the set of points where t is equal to s of d phi squared. This is equal to okay. So just to tell you what I mean by this notation, just in order to not have to keep writing the sum of squares of all first derivatives, I'm just going to write it like this. So when I write this, d phi squared, what I really mean is this, and I'll just write it out the first time. Okay. So this is the basic energy estimate. And one thing you can sort of immediately see by just applying Holder's inequality appropriately is that this implies the following. So I'll maybe I'll write it like this. Sigma s. Okay. So this is maybe, uh, a common way when first studying nonlinear wave equations. For example, if you're proving local wall posedness, this is often sort of the result of the energy inequality that's used. Okay, great. So energy estimates are important for this theorem in all cases because you want to show, that this sort of L2 based energy quantity stays bounded. So at this stage, you take the equation. Sorry. So remember, we're dealing with equation 1. You take this equation, and I'm tempted to just apply this energy estimate here. And what I end up seeing is the following. So one thing to ask yourself, sort of from the beginning is, could the energy estimate, even in principle, be enough to establish this result? And the answer is pretty clearly no. There are a lot of reasons why. But one thing you could do is you could just consider a very simple example. This equation here. So the difference between this equation and the wave equation is just that this equation satisfies no dispersive properties. You can sort of explicitly see how solutions of this equation behave. If you want something even simpler, just to be really, really, concrete, you can even just consider this, which sort of at some level formally looks like the other one. But you can just compute explicitly that solutions of this in general will blow up in finite time. So you have to use, and of course, this also satisfies some kind of energy estimate. So there's no way that that's sort of just that information is enough to, to establish the result that you want. So, energy estimates are great, but they don't really see the difference between solutions of the wave equation and something like this. And you need something that does. And So sort of the key difference that you don't see just with energy, sort of regular energy estimates, are that wave equations have dispersive or decay properties. So if you took, an introductory course on PDEs, you saw the Kirchhoff formula. You can directly see from that if you have smooth, compactly supported initial data, for example, your solution should pointwise go to zero at a certain rate, particularly like 1 over t in 3 dimensions. Just because, this is a useful way to sort of see what you could expect in general situations. It also pays to compute what's going on in spherical symmetry. And if you write the wave equation in spherical symmetry, reduces to the following. And you can then introduce coordinates. Which are very natural because they track the characteristics of this equation. You introduce these coordinates, you multiply through by r, and you can see that this is equivalent to the following equation. So if you'd like, showing that this is the case is just an algebraic exercise for you. And if you assume you have smooth, compactly supported initial data, for example, so this here is this is the TR plane and this is t equals 0. So your initial data is supported in here. Using this equation, plus the fact that along this axis, you must have that r phi vanishes. Because, just because r does, and phi should be a smooth function. You can compute very explicitly the solution of this equation. And when you do it, what you sort of see is that there's some region that looks like this. The solution is 0 here, 0 over here. And in this region here, it behaves like 1 over r for large r. So if you'd like, that's another exercise. It's very simple, but it's useful to go through, a simple equation. You can do it with a method of characteristics. All right. Okay. So this behavior, is very different from the behavior of this equation, and that's what you want to leverage. And if you look at this picture here, what you can sort of see is that at time t, the profile of the solution looks as follows. Again, this just follows from looking at that picture there. There's an annular region of thickness about t, or I should say radius about t, and thickness about 1. So this, the difference between the radii here is about 1, and this is within sigma t. And the solution has 2 properties. The first property is it's essentially supported just in this annular region. And the second property is it's sort of smeared out across the entire angular region. All right. So this is sort of the property that you'd like to say holds for solutions of this wave equation, but we're not making any symmetry assumptions. So sort of this symmetry consideration is just, it's to tell you the behavior you would like the solution to have. So the second tool, these weighted Sobolev inequalities, you can think that the basic idea with this, so tool 2, is to leverage symmetry properties. So a basic question you might ask is, you did this in spherical symmetry, where you could really compute things sort of very explicitly. To what extent does this survive if you're not spherically symmetric, but you're close to spherically symmetric? And that, the fact that you can, leverage something in this case is exactly what we're going to use. So you can think that well, I'll tell you what the motivation for this is a bit later. So I'm going to consider a family of vector fields consisting of the following things. So the most basic ones are translation vector fields. By translation vector fields, I mean they're generators of translations along coordinate systems. So these are things like, partial t, partial x, partial y, and partial z. You also have generators of rotations of space. And these are things like x dy minus y dx, and sort of, the analogous versions with the other spatial coordinates instead. For example, y dz minus z dy. And what you can sort of notice is, just thinking about Minkowski space. This is a wave equation on sort of the Minkowski space background. These things are special because they generate isometries of Minkowski space. And because we're going to leverage that fact, the fact that these things generate isometries of Minkowski space, let's just throw on some other isometries of Minkowski space. So these consist of the boosts. So these are things like t dx plus x dt. And there are other vector fields as well. T dy, just change the spatial coordinate here. And finally, I'll add in a vector field which it doesn't generate an isometry, but it generates a conformal isometry. And this is the scaling vector field. So you can think that all this is motivated just from this picture. Like, you did an explicit computation in symmetry, and you want to understand to what extent can this hope to survive outside of symmetry if you're still somehow perturbative off of that symmetry class. And the point is, the wave equation propagates spherical symmetry, which is saying that, rotation vector fields applied to your solution are zero. And the basic idea is that because rotations generate isometries, it turns out that there's a quantitative version of that. Meaning, if rotation vector fields applied to your solution are initially small, that should always be true. So, I'll say applied to data. So if you want to see that this is true, there are a couple things you could do. Oh, whoops. The first is just take a rotation vector field, or the same thing holds for any of these, which I'm saying here. I'll call any of them gamma. So gamma just means one of these vector fields, and compute the commutator of gamma with box. And what you'll see is that this commutator is in fact 0. Unless gamma is equal to scaling, in which case what you have is, I think it's either twice box or negative twice box, but it doesn't really matter. So what this means is, if phi solves a wave equation, gamma phi should as well. And it should solve a wave equation that doesn't look so different. That's sort of what you're banking on here. So one thing I should say, by the way, is if you're not, sort of so sad, trying to motivate how it is that you might come up with these, it's not so difficult to just directly algebraically check that these commutators behave in this way that I said. You can do it yourself. But if you'd like sort of a more general geometric reason why, you can sort of write the box operator in a more geometric way as being the divergence with respect to the Minkowski metric of d phi. And more generally, you could consider this for an arbitrary metric. This is sort of the version of the Laplace-Beltrami operator for the wave operator. You just take the divergence with respect to that metric of d phi. And the fact that these are generators of isometries is the same thing as saying that they're killing vector fields. Meaning that the following is true. Okay.
Scaling's not killing.
Yeah, that's right. Let's take it for gamma not equal to scaling. So if you're sort of more, comfortable with, geometry, a very general and sort of easy way to see that something like this should work is just the fact that if gamma generates Fs, so by Fs here, I just mean the flow map associated to the vector field gamma, then we can write the following, sort of running out of space. Just write this over here. So if gamma generates the flow map Fs, then, well, in fact, this is true for any flow map. You just always have the following identity. The pullback of box G applied to any function is simply equal to box with respect to the pullback metric applied to the pullback. All right. If you have a killing vector field, this is, just the same as G, right? And so then just differentiating both sides of this expression sort of manifestly gives you the identity you want. And this is totally general. Doesn't depend on the metric. Okay. All right. So as I was saying, if phi solves a wave equation, then gamma phi should as well. And what this means is that for those vector fields, for that large class, the hope we have is that energy estimates, which is something that applies to solutions of the wave equation, they don't just apply to phi, but they apply to gamma phi, all of those vector fields gamma. So for some multi-index alpha, which hopefully you've, I mean, if you haven't seen this, this basically just means I'm applying a string of those vector fields. And exactly which ones I'm applying is contained in this sort of array of positive or non-negative integers. So for a string of vector fields, we hope to have control over this is sort of the bet we make. We're hoping that for solutions of, the original wave equation, the energy doesn't grow too much. Now, because gamma commutes with the wave equation, gamma phi also solves a similar looking wave equation. So the hope is that the energy of those also don't, increase too much. It stays about the same as what it was initially. So the weighted Sobolev inequality comes in from the fact that you're going to leverage the fact that these vector fields gamma have weights. They have weights in their coefficients in order to show that this behavior here persists outside of symmetry. And so this behavior, just to remind you, is the profile of the solution is that it looks like it's roughly supported in this annular region here. And moreover, it's roughly uniformly smeared out across the whole sort of annular region. It's not really localized, say, there. Okay. So we have the following result. I mean, this is sort of called Kleinerman's Sobolev inequality. It says the following. And I'm just going to write this in 3 spatial dimensions. So the absolute value of f. So let me write this out and then I'll explain exactly what I mean. Okay. So just because it's a little bit more convenient to write it this way, I'm taking sort of spatial polar coordinates, meaning that r and omega are just polar coordinates on R3. I'm keeping the time coordinate t. And what this tells me is that for any function f, let's say smooth, compactly supported, on R4, you have the following inequality. Let me define this. This is just equal to. Oh, okay. So you have the following inequality. The point of this bracket notation is that t plus r, when you take an inverse power of it, is very bad around t equals 0 and r equals 0. It's dividing by 0. So, I just want to smooth it out there. The important thing is that for large t and r, this behaves like 1 over t plus r. And similarly, you have this factor of u here, which I'll just remind you. I mean, this was one of the coordinates introduced in spherical symmetry, which was equal to t minus r. And you can see that this sort of exactly tells you that the profile of the solution looks like what you can explicitly compute in spherical symmetry, right? The reason for this is because in this region here, u is approximately equal to 1. So, this factor here is about 1. Of course, in this region here, T and R are comparable. So this is basically saying that in this region, you're roughly equal to 1 over R, which is exactly, what you can compute happens for solutions of the wave equation there. This factor of U starts to kick in when you go in deeper here. When I come in to a region where, say, U is comparable to T, what I have is that the solution is much, much smaller than 1 over T. It becomes of size like 1 over T to the 3 halves. So this is, in the spherically symmetric, well, I mean, this is true for the homogeneous wave equation in general by the Strong-Huygens principle, but in the spherically symmetric case, it's very simple to see that the solution is 0 here. This doesn't tell you that you're 0, but it tells you that you're smaller. All right? Okay. So, so let me just sort of discuss the proof of this fact. Uh, the main driver is a rescaled Sobolev inequality. So here's sort of a general lemma, which in some ways is a bit simpler, but it's sort of like the reason why this is true. So I'm going to assume that I have so that this is, let me. This relies on a general result in Rn. So here's the lemma. I'm going to assume I have a collection of n numbers, which are assumed to be greater than 0. There's a collection of n numbers greater than 0. Under this assumption, what I can say is the following. The L infinity norm of F on Rn, where now x means just the regular coordinates on Rn, is bounded by some constant times the product from I equals 1 to n of the Li's to the negative 1/2 times the following. Okay. So this is sort of a version of the Sobolev inequality, where instead of assuming that I can take a bunch of derivatives of my function and put them in L2, and I want to get an L infinity bound out of that, I actually want to assume that instead of taking a bunch of unit scale derivatives, I have these numbers all greater than 0, which I think of as denoting a scale, and I can take weighted derivatives where Li denotes the weight I can take in the ith direction. All right. So what this inequality is basically just saying, I want to prove an L infinity Sobolev embedding theorem, just like the regular one that you learn in sort of a functional analysis class. But on the right-hand side, instead of regular partial derivatives, I want weighted partial derivatives where the weights are determined by these Li's. All right. That's sort of what I've written here. These gamma bars, which I've written to just sort of make it look kind of like these, They're the same as the coordinate partial derivatives, but they have these weights. All right. So the proof of this lemma is sort of it's very straightforward. This really is just a rescaled Sobolev inequality. And you can think that trying to play around with rescalings like this is motivated by the fact that you can turn, profiles of functions which are close to extremisors of the Sobolev inequality into things which are close to extremisors of this inequality, meaning sort of what's the best constant you can get here, and vice versa. All right. So I'm just going to reduce to the regular Sobolev inequality under that observation. Extremisors of one or near extremisors of one should give me near extremisors of the other. And so this seems like a natural thing to do. So I'm just going to, define a new coordinate system, which I'll call x bar I. And all that I'm doing is rescaling the coordinates by Li. There's no sum there. I'm rescaling every coordinate, making its level sets sort of Li spaced apart from each other. All right. When you do this, the first thing to note, so let, then just by the chain rule, what you can see is that the coordinate partial derivatives exactly become these sort of operators gamma bar. So this means that partial f over partial s bar I equals gamma I bar. And now you can just sort of proceed. So what we want to estimate is the L infinity norm of f relative to the coordinate, that you sort of the given coordinates x. The rescaling doesn't change the L infinity norm. Like if you look at the L infinity norm relative to the x bar coordinate system, it's the same. And now I can just apply the standard L2 based Sobolev embedding theorems to this function. But when I do that, when I apply the standard L2 based Sobolev embedding, I do it with respect to the Lebesgue space defined in the x bar coordinate system. So by what we already said, yeah, these partial derivatives here correspond just to the gammas, which are what I have control over. And the only thing I have to do is I have to understand how other LP space. So here I used how L infinity transforms under this sort of anisotropic rescaling. Here I just have to understand how L2 transforms. And, it's exactly this factor which pops out. So this is then equal to product. Right. So now it's the x coordinate. Sort of this is exactly what you wanted to show. Right? Okay. So, now, Kleinerman-Sobolev inequality has, there are sort of, you just have to massage this a little bit to really turn it into a proof of Kleinerman-Sobolev inequality. There are two main differences. The first is that sort of relative to the usual Cartesian coordinates, the vector fields aren't well aligned with those coordinates, right? In other words, they don't look like coordinate partial derivatives, whereas these are all coordinate partial derivatives. The other difference is that the weights aren't constants. They vary. But you can fix both of these issues. So I'll just tell you in words. Or I'll just outline it for you. So for what we want, we just have to make two modifications. The first modification is pick coordinates well adapted to the vector fields, meaning they'll look like coordinate partial derivatives if you massage them a bit. And a good I mean, there are a lot of choices, but one choice of a coordinate system is TU omega. So this is sort of a modified modified, polar coordinate system where you replace R with T minus R. All right. And then the final thing you have to do is to just localize in regions where the coefficients are roughly constant. In other words, you break up the inequality into places where T is between some factor of 2 of a given number. And you can then approximate the vector fields by constant coefficient vector fields, which is, what you have in this lemma, and then just directly apply the lemma. So localize to regions. Where the coefficients are roughly constant. And then, as I said, you've really now massaged everything to make it look like that. And you just apply the lemma. And you can now see how this might come up. Because here, in 3 dimensions, this sphere is 2-dimensional. Meaning you have 2 directions with a weight comparable to R. And, each direction gives you, the weight to the power 1/2. There's just one remaining direction. And it takes a little bit of algebra to see that the vector fields give you this direction only with a weight of U. So there's 2 directions with a weight of R and 1 direction with a weight of U. And that's exactly what gives it to you. Okay. Yeah, we're going over, right? Okay. Okay. So let me just try to outline for you how, you can combine this with energy estimates to prove the stability theorem. The main remaining thing that you need is to understand what a bootstrap argument is. Also, if there are questions, you should stop. Oh, wait, actually, there are other boards. Okay. So I just want to sketch this for you, the proof now goes a lot the same way as the proof of local well-posedness for, a nonlinear wave equation, which you might see in a PDE course. And if you've seen these sort of energy-based proofs of local well-posedness, then you might remember that you differentiate the equation. And on the right-hand side, there's always going to be some term with more derivatives than the others. And that's sort of the term you have to be most careful about. So this proof still has that feature, but I'm going to ignore it. All right. I just want to describe, what the difference is that comes from this. So this is the equation. I commute with gamma alpha. And the right-hand side is going to have things that look like this, right? So I'll just remind you the basic energy inequality that I'd shown. What that would tell you is the following. L2 of sigma s. Right? And I'm ignoring everything else. Now, here's what I sort of expect. If I look at this term here, this, and I just apply some Holder's inequality to this. All right. The important thing to note is that this starts to look like the energy norm, which I expect to be bounded, times something which should decay like whatever two sort of a quadratic expression in first derivatives of phi behave. And I have to integrate that in time. So this is given by data. And this here looks something like the following. So it's something bounded times t to the minus 2, and I have to integrate it in time. The reason it's t to the minus 2 is because this sort of, Heinerman-Sobolev inequality gives me the expectation that each factor decays like 1 over t. All right. So this schematically looks like I've won. Because this is sort of telling you that you have hope that the nonlinearity only pumps in a finite amount of energy into the system. In order to make this rigorous, that's where you have to use a bootstrap argument. Oh, actually. And here's the basic principle. So I'm just going to assume that I have, so this is sort of the general principle that makes bootstrap arguments work. Let A of t, B of t, and F of t be continuous curves. This t now is just, a variable. It doesn't really have anything to do with, the t there necessarily, but you often bootstrap in t, so it's sort of reminiscent of that. So here are the assumptions I'm going to have. The first assumption I'm going to have is B of t is strictly less than A of t for all t. The second assumption I'm going to have is that f of 0 is less than b of 0. And the third assumption I'm going to have is I'm going to assume that the following statement is true. If f of t is less than or equal to a of t, then f of t is less than or equal to b of t. And the conclusion is that f of t is less than or equal to b of t for all t greater than or equal. Okay. So an exercise for you is to prove this rigorously, but let me show you a picture that sort of tells you that this must be the case. Maybe this is the graph of a of t. Maybe this is the graph of b of t. And maybe this is the start of the graph for f of t. The only way that f of t could, if f of t starts to get too big, it must eventually cross. And because there's a gap between I'll just give you one way to make this work. The bootstrap assumption is basically your specification of the curve a of t. So the bootstrap assumption is going to be something like this. All right. Note that I actually expect my energy to be of size epsilon, so I'm sort of giving myself some space. That's like the condition that you have a little space between the two curves. The recovered bootstrap assumption, meaning sort of the curve b of t, which is sort of called recovered, recovering the assumption. In other words, what I'm going to show is that d gamma alpha phi is less than or equal to epsilon. Maybe I'll say some constant times epsilon. All right. So this is sort of my curve a of t. This is sort of my curve b of t. And for epsilon small, this curve lies below that one, strictly below it. And so you can apply that general principle. So this is how you can see that bootstrap assumptions are important because, at this step, this is sort of where I would be recovering the bootstrap assumption. Note that by data, or by my assumption on data, the first term will be less than or equal to epsilon because it's an assumption on data, right? This is where you have to use the bootstrap assumptions, but this is where the fact that it's nonlinear helps you because you end up getting a very large power of epsilon. And the behavior of this dominates the behavior of that for epsilon small. Okay. All right. So I claim with that, you can make the proof work. All right, yeah. Any question, or anything?
Let's think, John. Maybe due to our time constraints, let's can ask John questions during the break. Let's jump out for supposedly there's coffee, but